So, what we have seen so far was scalar changes of the pH caused by some chemical reactions like sulfate reduction, nitrate reduction to ammonia, and so on. We have seen effects caused by proton symport with sulfate, but unfortunately we couldn't discriminate between electroneutral symport with 2 protons and electrogenic transport with 3 protons. What was the reason? Because the membrane potential pulled back the electrogenic protons very, very quickly. And we have learned we need to assume that there are more than 99% of the protons of the electrogenic protons taken up within a second. And that makes it so difficult to see the most common event in a cell, that a proton is translocated electrogenically over a membrane. And what can we do? So what we do is we neutralize the membrane potential, and then we can see the translocated, the electrogenic vectorial protons. And there's a trick that we can use. And this trick is named KSCN. That's a chemical name. It's a potassium thiocyanate. Don't mix it up with cyanide. And this is a salt, simple salt, dissolves to K plus and SCN minus. And the SCN minus anion is membrane permeant. And it distributes over both sides of the membrane and compensates any electrogenic transport. Here's the scheme. So we have learned that there are some 30,000 charges generate the membrane potential of 150 millivolt in a bacterial cell. And we add up to 100 millimolar, so quite a lot of this thiocyanate. And we wait for some time, and then it has distributed over the membrane, inside and outside. And now, if any electrogenic thing occurs, some SCN minus ions will migrate over the membrane and compensate that. That means the membrane potential is not there anymore, but the delta pH, the pH gradient, that is still there. And if we add this into our assays, the curves are looking quite different. Here is a curve taken by Jan-Ole Reese, and it's nitrate reduction in H2 saturated KCl with thiocyanate. And you see the curve looks quite different from what we had before. It's a peak upwards. And finally, there's still alkalinization, and the alkalinization is the same as before. Actually, the peak doesn't look like that good. We had a very fast pH electrode, and obviously the HCl was added with a syringe very close to the tip of the electrode. And then in the first seconds, you have an increased concentration there, and you have to wait some time until it's getting the real value to compensate the scalar effect. And now comes the simulation. I'm going to show you how this looks like. Here's our PROTON.EXE, and we say show graphics. And what you see is here we very nicely can simulate the situation. So, and then we would like to look at our parameters for simulation and what has changed. So there's one thing that has really changed, and this is the ATPase rate. And this is not 99%, it's actually 1.5% 0.015 is 1.5% instead of 99%. And you can see that this difference is really relevant. And if I make it here, let me say it 10 times higher, you can see, oh, most of the effect is already gone. And if I make it 95, you can say, yeah, it's completely gone. It's a different time scale here, but it's looking like our previous very first experiment where we only see the scalar effect. The scalar thing doesn't change, but the proton translocation is not visible anymore. And now let's go back to the, I forgot what it was, 0.15, yeah, 1.5%. Okay, so what happens to the membrane potential? I could show it here as a graph, but we are looking into the numbers here, and we assumed to have a minus 150 millivolts, and you can see when we have here after 2 minutes 120 seconds we have this pulse added. We can see that the membrane potential is really increasing to values of about 5. No, I lost it. Sorry, there. It's no. It's here 32, 33, maybe even more. Let me look. It's 35,000, 38,000. I think I found 50,000. Yeah, it's 50,000 millivolt or 50 volt. That cannot happen. We have shown recently that even a natural increase of the membrane potential makes a membrane leaky. They never can stand 50 volts. Normally they have 0.15 millivolts volts at maximum. And therefore we very effectively have destroyed this membrane potential. And fortunately, this parameter is not a driving force for running the simulation, but it's only indicated what would come out. And if we increase here to 95%, okay, then we wouldn't see this anymore, but we would also see the membrane potential doesn't increase that much. You can see it's here 400, which still is too much, much more than you would expect. So you will have this 95%. And that really shows that the membrane potential is the major player. Then the pH, the delta pH, doesn't change. The cells are very well buffered. The membrane potential is the major buffer, the major player, and prevents that we see the most common event in a bacterial cell.